Okay, good afternoon. All right, let's start. The last time we looked at the equation for the CMOS inverter delay. Delay time tau d, C times VDD, that's the charge, Q. Q divided by the current give us the fall time and rise time. The average of the force time and rise time give us the delay. All right? And the other factor of 2 could be interpreted as saying that only half of the VDD swing is needed. And the power of CMOS basically is C times VDD squared times the frequency of the switching. Okay? One thing we did last time is to show that just for the purpose of minimizing the this delay time, one can argue that WPWN ratio should be 1.5. Well, it turns out if you want to minimize the product of the delay time and power, you can show this is also the right ratio of WPWN. Okay? There are two other slides that we did not use last lecture. Let's just briefly go over those. I would not necessarily go through the entire derivation. And so 2 slides before this is slide 1616. Now there, what we're plotting is we're looking at the other question, another question. The question is how. So we know the ratio of W and WP, but how big a WWN and WP should we use? All right, ratio is one thing. We're already settled on that. It could be 1.5, could be 2, right? Then how large a W's should we use? Well, turns out using the equations that we introduced the last time, using differentiation to try to minimize things, or in this case we don't even have to minimize anything, I guess I'm just plotting it. You can show that if you look at the delay time decreases monotonously with increasing W. In other words, using larger W always helps. The reason is basically this. Tau has to do with proportional C and inversely proportional to I, right? I'm not including things like VDD, right? Right, and 4. So if you increase the W by a factor of 2, is that right? I will increase by a factor of 2 always. I is always proportional to W, is that right? Yes? C, on the other hand, does not necessarily increase by 2, because C may be equal to some kind of capacitance that's independent of the W. Let's call the C in, implying this interconnect. Well, maybe that's the best way to call this interconnect. Things that are not proportional to W plus something that let's call the C prime, then times W. There are certain capacitances that are proportional to W, such as the load capacitance of the gate, yes? Or the driver's capacitance, yes? So just because of that, when you look at the ratio between those two things, then increasing W is always better. For example, if W goes to well, this is always better. I guess it is better. Maybe it's not so easy for you to see this relationship. But increasing W is always better, okay? Always reduces the delay. So if your goal is only to reduce the delay, then just use as large W as you want. But in reality, that's not the only consideration. You will consider at least one is the density, how much real estate you can afford to use, which we're not talking about here. The other thing is energy or power. If you use large transistors, you have large capacitances, then the power dissipation will be large. Is that right? So if we now say we're trying to look at the product of delay and energy. Energy is just VDD squared times C. Is that right? If this is what we're looking at, what turns out is not monotonic function of Wm plus Wp anymore. It actually shows a minimum. At some point of W and WP, the energy delay product is minimum, all right? And the minimum happens to happen at 0.5. So let's look at a horizontal scale, what we're plotting. What's the scale? The scale is the driver device capacitance as function of total C. Maybe I shouldn't say driver capacitance as a function of total C. Let me just say the capacitance which is proportional to W, shall we say? All right. The capacitance that is proportional to W. For example, if you insist that when driver capacitance is enlarged, the load W also is enlarged. If you enlarge the driver device W, you also enlarge the load device W in proportion. If you insist on that, then I should really just say driver device and load device. So let me rephrase this. I think this is a better phrase. Is really this. Is the W dependent capacitance, all right? This is the W dependent, which really means W proportional. Let me call this W proportional. W proportional capacitance. In other words, in the capacitance, the part is proportional to W. So when the part that's proportional to W is 1/2 of the total capacitance, in other words, when the interconnect capacitance and the W proportional capacitance are equal, that is when the delay energy product's minimum. Now, I'm not trying to emphasize this point to you because there's no particular reason to think that this is the product we want to minimize, right? It's just one possible metric, right? I could try to minimize tau squared times energy, or I can try to minimize tau times energy squared. Is that right? Okay. But just so happens, if you try to minimize this, you can show that when the W proportional capacitance is equal to the W independent capacitance, then that's when you minimize it. Okay? So there's some simple relationships. Okay? All right. And the other remaining slide, I will not spend much time. I'll let you think through this. But in a similar manner, when you think about oxide thickness, do we really want to increase or decrease the oxide thickness? Turns out there's also a minimum for delay and minimum for the delay energy product. Just look at it, minimum for delay. The horizontal scale is the total oxide capacitance as a function, total oxide-related capacitance as function of as a fraction of the total load capacitance. Let me just rephrase this. Total capacitance, right? Total C. We have been using C to represent all the capacitance. But among within the C, some of the C is independent of your gate oxide thickness, such as interconnect, such as junction capacitance. Is that right? Yes. Another part is oxide thickness dependent. So why don't we call this oxide thickness dependent, right? Oxide thickness dependent. Oxide dependent, oxide thickness dependent. Yes? Oxide thickness dependent. Capacitance as fraction of the total C. Well, you can show that when the oxide thickness dependent capacitance is half of the total C, you minimize delay. If you make oxide thinner than that, then you actually will prolong the delay because the current is not increasing as fast as you are increasing the capacitance. All right? Okay. There are certain assumptions behind this. The main assumption is what the approximate relationship that we introduced last time. This ID set is proportional to L minus 1/2 and Tox minus 1/2. Remember that? All right, it's approximation. But if you use this kind of approximation, you can show that there is an optimum for this oxide thickness. That optimum, on the other hand, is dependent on the composition of the load capacitance. Now, for example, if there were no interconnect capacitance, all right? If all the capacitance is dependent on oxide thickness, which of course is is nonsensical because there's always some junction capacitance, something like that. But if in that very special case, right, then what are we saying here? Well, I guess that means we don't have any choice. So this is not interesting, all right? So this curve will be meaningless if you don't have any capacitance that's dependent on outside thickness. So if you have some, okay, let's put it this way then, all right. Suppose this is a circuit that's heavily loaded by interconnect capacitance, right? Since you're trying to put the oxide-dependent capacitance at equal to the interconnect capacitance, right? That's what this point means. So in a heavily interconnect loaded circuit, you want to use thin oxide. Is that right? Right? And if there's very little interconnect loading, just junction capacitance is the only oxide-independent capacitance that you're going to use thicker oxide. Is that right? Unfortunately, the technology today don't give you that choice, by the way. All right? You get only one capacitance oxide thickness to drive all kind of gates. So you can, again, think in the future, when we really want to try even harder to get the capacitance up, get the power down, maybe we could even introduce more than one oxide thickness, right? We already decided that we can tolerate more than one threshold voltage, remember? Why can we not tolerate more than one oxide thickness? Now, it's not happening yet. The cost doesn't seem to be acceptable based on the gain that one can get that. But you can see this is where this concept can be understood, right? That's what I'm saying. All right. Okay. So the next topic I want to discuss with you really is extension of the first few slides that we look at. So interconnect certainly is a big question in terms of the circuit optimization, circuit performance. And this course has to do with transistors, so interconnect is not a main topic, but just because it's an important topic, I think we're going to devote the rest of today's lecture to look at that issue, all right? Now, unfortunately, the type size on this slide is too small, so I don't expect you to be able to see that on the screen. If you can turn to slide 17-1, that's great. If not, I can just highlight what I want to point out for you. In the slide, and this is again a one page from the International Technology Roadmap of Semiconductor Technology, okay? It used to be called the National Technology Roadmap for Semiconductor, but just last year it has enlarged to incorporate international members in this effort, so it's now known as International Technology Roadmap of Semiconductors. Now, the different columns represent either time or different technology node. It's measured in units of 250 nanometer, 180 nanometer, 150 nanometer, 130 nanometer, 100 nanometer, and this may be called 0.1 micron technology, all right, and 0.07 and 0.05 micron technology. What I want particularly to highlight is a few things. If you cannot read, I'll just read out for you. Let's see, what are the items that I wanted to read out for you here. Okay, yeah, the third level is what I want to read out for you. The number of metal levels. Actually, let's read the second or third line here. Second, if we don't count the heading of the rows of the columns. Then the number of metal level using logic circuit increases from 6 to 7 to 9. So we're using more and more metal layers for logic circuit. For memory product, the metal layer is from 2 to 3 to 4. All right? So there's more and more interconnect layers, and that's another indication of the importance of interconnect, not only in terms of impact on the performance, but also impact on the cost of manufacturing. All right? And so why don't I just move on to the next slide? Don't look at the small typing. We'll come back to some of these issues listed in this table. We will do that, all right? We'll not refer to the table specifically. All right, when we look at interconnect, there are a few things I want to just introduce to you. One is called electron migration. Electron migration is a reliability issue. All right, we said when we talk about technology scale, we have to guarantee reliability. So one of the reliability issue with interconnect is called electron migration. What that means is that when electrons flow through the interconnect, it can give some momentum to the metal atom and therefore cause metal atom to shift. And as a result, voids, holes can be created in the metal and the resistance increases. In special cases, you can even have open circuit, but usually the failure is caused by increase in the resistance. I will give you one example. That's what happens at a via. The bottom of this page shows two metal layers. Let's consider the bottom layer M1, meaning for first layer of metal. The second layer is called M2, meaning the second layer of a metal. Between two layers of metal, of course, we have some dielectric to insulate them. Holes are etched through the insulator in order to make interconnect or to connect the first and second layer of metal. Right? And we do this by etching a hole through this dielectric known as the intermetal dielectric, by the way. They're called intermetal dielectric, sometimes called IMD, dielectric. So we will etch a hole through the intermetal dielectric that's before metal 2 has been deposited. And then we'll fill that hole with tungsten. All right? Okay? After that's done, then we deposit the second layer of metal over both the intermetal dielectric, of course, also covering this tungsten. We call this a tungsten plug, sometimes called tungsten via. All right, tungsten plug, this tungsten via. And then we use lithography to define this metal 2 pattern. So this is how we connect metal 1 and metal 2. So let's assume we're looking at this case. If we pass current from metal 1 to metal 2, in other words, if the electrons flow from metal 2 through the tungsten plug, through this metal 1, let's call it aluminum. After a while, if you cut this structure and then look at it using SEM or TEM, what you will find is that a void would appear here. What happens is that aluminum has much higher mobility than tungsten. So aluminum will be pushed by the electron along the direction of electron flow, but tungsten doesn't move. All right? Okay? So you're going to have a void, a hole. Can you see that? Can you see that how can increase resistance? And in fact, this can even give you a sort of a positive feedback in that, you know, there's less contact here, there will be a larger current density, and this is going to even happen more. Yes, Tori. Why tungsten? Well, turns out there are some subtle reasons. Maybe I'll mention the subtle reasons later on, but I'll give you more sort of obvious reasons. Well, it turns out that tungsten itself has a better reliability than aluminum, all right? And in the via, sometimes we are concerned about the current density in the via itself, so tungsten is good. Tungsten deposition in the via hole also historically was studied very early on, has worked quite well. And so people like to use tungsten, so tungsten continues to be very popular. But actually, I should tell you that in the research literature, you will find there has been a lot of effort to develop aluminum for via. And in fact, there are even reasons to argue aluminum via can be or may be more reliable. Okay? If it's more reliable, it's because then this whole aluminum simply flow. Then you don't have this heterogeneous interface that actually can be more reliable. But let me also, I will not go into detail, but tell you there are also subtle reasons to argue actually we do want to stop or break up the metal periodically by adding a barrier for electromigration. Because there's some reason to think that if the aluminum line is short enough, all right, short enough meaning it has on one end is blocked by, say, tungsten, so there's no supply of aluminum. On the other hand, blocked by also tungsten, so there's no place for aluminum to flow. Then aluminum will not move. Okay, just like a pipe that's sealed, so the water in it will not flow. Okay, there's some reason to believe that that can happen, and so that's a subtle reason to actually want to do that. Okay, but certainly if you have a line that's fairly long, aluminum line, this is what you will see. All right. Now in this example on top, showing you this particular example after this metal line stress, it's quite surprising. The bottom is metal 1, bottom layer is metal 1, middle layer is intermetal dielectric, top layer is metal 2, and here we're looking at via, or where the tungsten plug was or used to be. Now you notice, and we're telling you this two light-colored position material is tungsten. The tungsten used to be here. Now it's no longer at where it was. This is because once this hole is formed, tungsten actually will be pushed downward because there's tremendous pressure built up by electromigration in metal 2. Can you see that? Metal is flowing toward this tungsten block. It actually pushes down. And not only that, in this case, actually broke the tungsten via into two pieces. So this should prove to you that electromigration is something very real. It's a very strong force, something very difficult to deal with. All right? Okay. Now, how do you improve that? Well, turns out one thing to improve that, and this is how everyone does it now. 5 years ago, 10 years ago, wasn't like that. But now people have learned the thing to do is don't just put the tungsten directly in contact with aluminum. Instead, put a layer of material. Very often we put nitride or tungsten, titungsten layer. Let's say tinitride, for example. And this material is a conductor, but has very low mobility, similar to tungsten, so it does not suffer from electromigration very much. In this case, even if some voids start to fill here, aluminum moves away from the tinitride interface, current can still spread, flow from the tungsten plugs through the tinitride. You see what I'm saying? Yes, flowing to aluminum. Or in this case, I'm showing the electrons flowing from metal 1 to metal 2. I'm sorry. So we actually expect a void to form here. All right? So in that case, actually a thicker tinitride would be on bottom of metal 2 would be desirable. So in this case, current actually can still flow through tinitride for a while before going into aluminum. You see that? So first of all, it avoids this positive feedback, creating a really bad void, and also even if this whole part is covered by a void, you won't get an open circuit. Is that right? Okay. So this therefore there's a refractory metal as a liner between the tungsten via and aluminum is very commonly used. All right. Now I give you this example, electromigration at a via, not because that's where it's the only place where it can happen, just because it's easier to understand why it happens here. In fact, it also happens in long lines. In fact, that's where people mostly are looking at. This is because in the long line, the electromigration happens mostly at green boundaries. Mobility of the aluminum is much larger in the green boundary compared to the bulk of the green. So suppose you have a particular point where you have several green boundary moving away along the direction of electron flow, and you only have one green coming in, or there's no green coming in, like in this case. You have several green boundary going away. Then there's very little supply of aluminum toward this point. We call this triple point. But several paths to take aluminum away from this point. that right? By electron migration. So guess what's going to happen at this point as time goes on? A void forms, is that right? So it's a kind of stochastic process depending on the microstructure of the aluminum line. Some point will start to form some voids. And of course, other points, aluminum will accumulate. Pressure will build up. Okay? Some that the pressure even cause aluminum to extrude, form a short across the intermetal dielectric. So electron migration is a concern. All right? Okay. And so what do engineers do? They do something called accelerated testing. So through enough experiments and some theoretical work, people decided the lifetime is a power law function of the current. And in fact, that power, most people believe, is a 2. All right? So lifetime is inversely proportional to the second power of current, or current density. So if you plot lifetime and the current in a log-log plot, you can get a series of curves. Let's say look at one curve with a slope of 2 or minus 2. In addition, lifetime is function of temperature because it has to do with electron migration, the mobility of the metal atom. Therefore, the higher temperature, the larger the metal mobility, the shorter the lifetime. You see that? So lifetime is a Arrhenius function of temperature, exponential Q over KT. Again, through enough experiment, people have decided a certain activation energy Q, for example, 0.7 volt for aluminum. For copper interconnect, this number is larger, perhaps 1.2 eV. So then you also can add different lines for different temperature, that's what I'm saying. And every point, any points on any of the set of lines actually refers to the same metal line, same material. Do you see what I'm talking about? Same metal line, just depending on the temperature and current density, it's going to have a different lifetime. You follow this? All right. In other words, if a line happens to have a few minutes of a lifetime at this high current density and high temperature, you can infer from that data point, just because at this many minutes, it is going to have this many minutes at a shorter, at a lower current density and a lower current temperature. Do you follow what I'm saying? So therefore, engineers take advantage of this relationship. They would design experiment where they get several hundreds of metal lines and stress them all at a fairly large current density, a fairly high temperature. Temperature and current is chosen so that they are going to see failure before too long. Before too long meaning without having to wait for months or years. That wouldn't give them the result soon enough. So they choose that condition so that they accelerate the failure. They see the failure within, let's say, days, and then based on that, they infer at a lower current density, at the current density the designer actually used the metal for, and at a lower temperature where the chip is actually going to be operating at, then whether this lifetime is going to be longer than, say, 10 years. So that's the way it works. Okay? All right. Actually, what really happens kind of reverse. The reliability engineer does not take the current density from the designer, but the reliability engineer perform this experiment first and come up with a number that's saying our metal technology is good enough for, let's say, 2 milliamp per micron square. And it gives this number to the designers. This is known as design rule. And the designer will have to make sure that the metal width is large enough so that current it does not exceed 2 milliamp per micron square, for example. All right? So this is how the metal reliability is determined. All right? So when the engineer chooses the testing condition, he has several choices. He can choose a moderate temperature and a moderate current density, and just sit there and wait for many days and maybe even weeks. The advantage of doing that experiment is that there's more confidence extrapolating a failure data that's several weeks to 10 years. Another choice, you can choose a very aggressive current density, a very high temperature. In that case, you can get an answer within minutes, truly. But then there's less confidence to extrapolate that data. We don't know whether the mechanism of electron migration truly remain exactly the same, or perhaps the activation energy changed when the temperature gets that high, or when the current density gets that high. You see that? So this is an issue the engineers often have to deal with. Obviously, if we're willing to spend 3 years to do the reliability test, then extrapolating that to 10 years, almost no-brainer, right? How much wrong can you be? But you have to trade that off that time against the confidence that you gain, okay? All right, here's an interesting picture come from TSMC. This is a logic process, has 4 layers of metal, and after the chip is done, you just dip the chip into acid so that SiO2, the intermetal dielectric, is all etched away. So what you see is the skeleton of this metal around. So you see the top one says metal 4, next is metal 3, and you notice between metal 3 and metal 4 there's a via here. It looks like a cylindrical post. That's not what the layout shows. Layout would have shown a square via here, but just because lithography, you end up with a round hole. Okay, so you can see we're coming to the very much the limit of lithography. We cannot resolve these corners anymore, right, at this feature size. And if you look carefully, you see those liners, those tinitride layers. Do you see that? Yeah? On top and bottom of each metal interconnect, you see this tinitride layers, all right? Okay, so this is what you see. We're talking about very complex 3D geometry, all right? And, okay. So, with this as the background, we now have to think that we're using a very simple cross-section to represent that complex geometry. And when we have these kind of lines running next to each other within the same level, or lines running over another layer. By the way, if there are several lines in the bottom layer, that bottom layer can be considered just as a continuous metal line as far as capacitance is concerned. This has been verified with solving the Poisson or the Laplace equation. All right. So we often model this capacitance as if the bottom layer is just a complete conductor rather than lines of conductor, all right? Here it says substrate. Substrate kind of implies we're talking about silicon as substrate. It's more than that. This could be metal 1 layer, and the 3 lines is in metal 2 layer, for example. Or this could be metal 4 layer. Those 3 lines are in the metal 5 layer. See what I'm talking about? So there are 2 kinds of capacitance we want to think about. There's the interlayer capacitance. Yeah. There's also the intralayer or interline capacitance, the capacitance between the neighbors. All right. The first thing is to say that this capacitance are well, let's say talk about the scaling. As a result of scaling, we have tried very hard to make this W small and make S small, so that we can pack many lines in this in the same layer, and especially in the lower layers, we have to do that because our transistor packing density is so high. In order to make contact with this many transistors, we have to pack the metal layer very dense. When we do that, unfortunately, the C12 becomes very large. All right, it's especially so because the height of the metal is not reduced in proportion because we're concerned about resistance of the metal line. All right. In contrast, this thickness of intermetal layer, we don't scale this intermetal layer very aggressively. We kind of have been able to allow this metal layer to stay around, 1 micron, half micron in thickness. We just try harder to develop the etching technology to etch that via through a relatively thick intermetal dielectric, so that we etch a small hole, but it's deep and small hole. So we developed technology to do that. As a result, C12 kind of has been kind of maintained, not very large. All right. So but all these capacitance should be considered. Now, why are we concerned about capacitance? Are they all bad? Well, certainly in terms of the propagation delay, it definitely, the larger capacitance, the worse. Remember, the delay time is proportional to C, right? So anytime you introduce capacitance, it doesn't matter what's to your next door neighbor or to the bottom or to the layer below, it's always going to make the circuit slower. All right? Now, what's interesting is, similarly, higher capacitance always increase power dissipation, because power dissipation is CV square F, so that's always bad. There's a third consideration, noise, or you may say crosstalk. That is, if a signal is applied to this middle wire, it's also going to capacitive coupling to its neighbor, right? So to its neighbor, there's going to be noise. If noise is too large, it's going to perhaps give you a wrong logic reading. If noise is that large, turns out it may have an impact on the delay time of this signal carried by this neighbor line, which, by the way, we usually call one the aggressor line and call another the victim line. All right, I like those names. I think they're very descriptive. All right? So a signal applied to the aggressor line will create a noise on the victim line. This can cause either a mistaken signal on the victim line, or more subtly impact the delay time of the victim line or signal carried by victim line. The interesting thing is that as far as the noise is concerned, it's not so obvious that capacitance is always a bad thing. Certainly, this capacitance is bad, right? We don't want capacitance with neighbors. But actually, this capacitance in some ways, or other capacitance to ground, is good. Because if this capacitance is larger than that capacitance, then we're not going to see as large a delta V in the noise being produced by the aggressor. Can you see that? Right? In other words, if there's no other capacitance applied to this victim, only this one capacitance between the two lines exists. Then if I pull this line from 0 to 5, guess what's going to happen to the voltage on this line? It's going to rise by 5 volts or so. You see that? Because there's nothing else to prevent it, to hold it to ground, let's say. So the only reason we don't see 5-volt noise on this line is because there are some other capacitance tied to it, other than another transistor tied somewhere else. This capacitance also tends to make this capacitance, this victim line, less sensitive to the aggressor signal. All right? Turi.
Are we making these comments sort of from a designer's perspective, or are you implying that one would literally try to influence these capacitances from a technology standpoint?
Both. I am speaking mainly from the designer's perspective, but technologists actually is very aware of these trade-offs, because technologists does have some control. You know, if this is a good thing, then maybe we should not make this two thing. All right? And if this is the bad thing, maybe we only want to minimize this. And I'll give you an example. People do make this kind of trade-off. For example, one thing that is being considered is to do this. We're going to do different kind of dielectrics. This dielectric continues to be SiO2, which has a dielectric constant about 4, all right? And then we're going to use a different dielectric between the lines. And we use dielectric with, we call it low K dielectric, with dielectric constant only 2. That way we can minimize C12, but does not change C11 too much. You see that? And this is because of realization that C11 actually helps a little bit in terms of noise sometimes. Now, if that trade-off is not there, then the technology is going to develop technology that's all low K, for example. So this information is transferred back and forth between technologists and designer. Yes?
I mean, the only thing one would add on to that is that some of these presumptions
That is correct.
The designer could just space the pitch slightly and dramatically reduce C12 because the designer was aware of the potential coupling. Like I'm wondering
Absolutely.
how much you'd want to leave this just to the designer to make the choice.
Definitely. Final choice is on the designer. What technologists had to do is, if, for example, in choosing this locate dielectric, where to put it, the thickness of the interconnect, and how hard you want to try to develop the etching technology. Do you really want to minimize the gap, or do you want to minimize the width of the metal? So the technologists have to make some decisions about the choices to invest in this effort, because after all, he's going to put down what's known as the minimum design rule. Within those design rules, then finally the design engineer can make optimization to his or her heart's desire. Right? But he or she will be limited by the design rule that the technologies give to him. So both sides have to work together. So at this point, then we want to talk a little bit about the clever idea to measure capacitances. How do you measure capacitance? After all, we're talking of extremely small capacitance, probably boggles the mind. You know, for example, the capacitance of a metal 1 line, minimum size metal 1 line, and the minimum size metal 2 line, they cross each other. What is the capacitance between at this cross section, right? Well, it turns out that's important to know, because this is the kind of information designer will want. All right, that's what's needed for the SPICE or for other circuit design tools to optimize the circuit. So how do you characterize that? The standard way of doing the standard straightforward way to do this: lay out a transistor test pattern with, you know, thousands of lines going left to right in metal 1, and thousands of lines going up and down in metal 2. So you form millions of these this little capacitance, and then measured with a probe and use a capacitance meter. It works, but it's a very area intensive, especially when you consider the kind of combination you can imagine. There are line layers, right? How many of overlap are you going to have? How about the neighbors? Are you going to use the width of the line as another variable? So how are you going to how can you afford this kind of a large capacitor's structure? Or so it's very difficult. Well, it turns out it's a very clever thing. You can measure very, very small capacitance, even actually the crossing capacitance between minimum size metal 1 line, minimum size metal 2 line is larger than this. So we can measure it just with one intercross directly, and this can be set up very easy. Only DC ammeter is required actually, and totally done on chip. No reference capacitance needed, and the result then can be used to validate and calibrate interconnect simulators. By the way, simulators still needed to account for this varied structures that you see in that TEM picture with oxide etched away. And this is also going to be useful for process monitoring. Is the capacitance really within a spec? And because these test structures are so small, they can be laid out in what's known as a scribe line between the chip, all right? So you don't waste the silicon area to do this process monitor. Now, how is that done? Well, we call this a CBCM. We coined this name. It's a long name, but let me spell it out for you. It's called charge-based capacitance measurement, all right? Charge-based capacitance measurement. Okay. Now, how do we do this? Okay. And I don't think this is in one of the reading material that I signed, but if you're interested in this, you can look that up. It's done this way. What looks like to you, let's just look at one side right now, all right? Just look at one side, just left-hand side, okay? What looks like is an inverter, isn't it? A P MOSFET on top, the circle indicated P MOSFET, N MOSFET on bottom, right? Connect between VDD and the ground, with this ammeter in between. So this is inverter, except for one difference. These two gates are not driven by the same clock. the two gates are driven by two different clocks, V1 and V2. All right, I'll show you. I don't show you. I'll describe to you the relationship between the clock in a moment. Okay, all right. They're driven by two different clocks. It's all right. All right. I guess I should show you on this side first now. Look at this side. It's better. It's the same thing. It looks like an inverter, but it's not because they're driven by two different clocks. Is okay? All right. And the only load that this test structure has is that small capacitance you're trying to measure. Here I'm drawing this metal 1, metal 2 crossing as an example. All right? Think of this as metal 1. It's connected to the output of this quote-unquote inverter-like circuit. Yeah? And the vertical line is the metal 2 line connected to ground. So the load is just the capacitance. You see that? All right? Now how does it work? It works this way. Let's say first you use a clock, V2 goes, well, I don't, let me use goes on and high and low a little bit maybe. Let's say first V2 go low. Instead of low, let me just say we first turn on this p-channel transistor. How's that? We turn on the p-channel transistor so the current start to flow from the VDD through p-channel transistor to charge up the C. This is unknown C here. Is that right? This is unknown C. Charge up the C. Okay? Right? You see we're using the same concept used in the last lecture about how inverter works, right? So when the p-channel is turned on, current flows from the VDD to charge up this capacitor. Right? Yes? So you wait long enough, because we're not trying to build gigahertz chip here. You can use only 1 megahertz or even slower if you wish. You wait long enough to make sure it charges to VCC or VDD. It's okay? Then you turn off this P transistor. And for a brief moment, both transistors are off. This is important because we're trying to avoid the short circuit current that we talked about last time, or the crowbar current, all right? So both transistors are off briefly. Then we turn on the N-channel transistor only. P remains off. Now what happens when we turn on N-channel transistor? This capacitor gets discharged. Is that right? After it's fully discharged, we turn off the N-channel transistor. Yes? After a while, so that there's no short circuit current, we repeat the process. We turn on the P-channel transistor again. So what we're doing is kind of a charge pump circuit. We pump charge into this load and then dump it. We put charge pump into the load and then dump it. In this case, what will the DC emitter read? Let's think about it. What does DC emitter read? DC emitter will simply read C, forget about C prime, we'll see what that means in a moment. In fact, let me just, let's read here, all right? It's to just read C is unknown C, forget about what C prime means. C is unknown C times VDD times F. Is that right? Because each cycle, how much charge is supplied by the power supply? C times VDD, that's all, right? There's nowhere else for the charge to go. It only supplies C times VDD each cycle. And every second we have F cycles. So therefore, charge times cycle is current. Remember that power, how we derive the power of CMOS circuit? That's how we get this average current. Is that right? Perfect. And so forget about C prime, continue. I just want you to try this experiment. So let's just say I is equal to C times VD times F. F is known because you applied the clock. VDD is known, you applied it. I net can be measured by an ammeter, therefore the only unknown is C. Is that right? It's very simple. Couldn't be simple enough. That's all you need. It's a clock which is generated on chip, by the way. So the students designed the chip, a simple circuit to generate this clock on chip. And externally, we only put a DC ammeter in there, right? Then we connect to VDDs. All right. So the remaining question is how sensitive it is. Is it? All right. Now remember, keep in mind, 10 to the minus 14 is actually better than the larger than the capacity we need to measure. All right. Okay. Let's see what we have. Well, you tell me some numbers. Let's start by let's say, based on what I just described, what kind of frequency do you think you can apply? Clearly, the larger the frequency, the more sensitive, right? You can measure C. What frequency would you feel comfortable doing what I just asked you to do? 1 mega is a good answer from the material scientists. I like to hear an answer from a circuit designer. How's frequency you feel comfortable? 100 megahertz, so that's real designer speaking. I don't care how much you want to use. Let's call 10 megahertz, all right? 10 to the 7th. Is that okay? Okay? All right. Now, voltage doesn't matter. Probably the usual VDD, right? Just to keep it simple, let's call it 1 volt, okay? We're not trying to squeeze anything out of this, okay? 1 volt. Is that all right? It's okay? Now, this is the thing you probably don't know, but I think you should know if you, take a course like this, talking a lot about characterization and transistor measurement. A good ammeter, I don't mean a particularly fancy one, just any, HP transistor characterization equipment. What do you think a good DC ammeter can measure? Some idea? What's that? Picoamp is a good number. The spec is usually 0.1 picoamp. All right, let's call it picoamp. All right, and we're not trying pushing things here. Suppose this is a picoamp, 10 to the minus 12 ampere. It's okay. Now, what C can you get? Can you give me an answer? Just by looking at this, I think you already know the answer. What's the C? 10 to the minus 19 farad. Okay. Now, what's the meaning of 10 to the minus 19 farad? We know 10 to the minus 12 farad is picofarad. All right, 10 to the minus 18 would be, 15 would be the let's see, pico and attofarad. Is that right? Okay. Sorry, is that right? Did I do this right? Femtofarad is 10 to the minus 15, right? 10 to the minus 18 is attofarad, it's AF. Okay. So this is even less than that. Okay. Yes.
As it's drawn, though, the restriction in sensitivity is not going to be just I and F. It's sort of that second line, the ratio of other capacitances.
Absolutely, absolutely. Now that you have seen, so it turns out this actually is not even a limit. All right, it's so small. Turns out what real limit is, we have some parasitic capacitance here, right? Right? But we can do that by trying to subtracting out by putting a reference here. So we always lay this out with a reference next to it. Now, circuit designer will know that transistor matching happens to be very good. All right. So we're trying to take advantage of that so that we actually have two structures. The only difference is that one have this capacitance, unknown capacitance, the other does not. You notice that? This one does not have a cross point here. It still has the usual junction capacitance, right? And the other is straight capacitance. Do you follow what I'm saying? Yeah. So what you do is you measure the DC current I from this structure and I prime from that structure. You take the difference between that two. That's what gives you CVDDF. You see what I'm saying? So now I'll let you articulate what is the real resolution limit of this technique then. What is the real resolution limit? If I can really subtract this parasitic capacitance out, then I don't have limit anymore, right? What do you think? What does that mean? That is delta CGF. Speak into the microphone, please. What is delta CGF?
Sorry, my microphone is broken.
Okay.
It's the mismatch of the parasites.
Mismatch is the word. All right. So for design, for circuit designers, mismatch is an important design limitation. At some point, it's going to limit what you can do. In this case, it limits that. So it's a mismatch. So what you do is you try to use a transistor that's not very large, not W. You don't need that because you won't have to be fast, right? So it's kind of close to minimum. You don't want minimum either because very minimum, maybe the mismatch is a little larger, right? So, the mismatch of the transistor parasitic capacitance is probably a small fraction of the transistor capacitance, maybe 1/100th of transistor capacitance. So if that's the resolution, is that good enough or not? Right? If the resolution is good to 1/100th of a small transistor capacitance, and if you're still not satisfied, well, that will be a little hard to see what impact it will make, right? When the intercontact capacitance is only 1/100th of a small transistor's, say, junction capacitance or overlap capacitance, you better be satisfied with that. So this turns out to be a very good technique, and so the design community have proposed to actually use this as a standard in the industry to calibrate the design tools, because we can have capacitance models and capacitance simulators, but finally we still need experimental verification so that we know whose model is right, who's better, and whether the model can be counted on to give us a good design accuracy. All right. So here are some raw data of the measurement. You will see that net current is proportional to VDD, as expected, proportional to frequency. So there are a lot of easy way for you to check the sanity of this technique. Okay? All right. Yes, question?
Yeah, you sort of answered that, but
yes.
During every cycle, the amount of charge that flows is 1 electron.
Yes.
And it's just hard to believe that you can resolve 1 electron moving in and out.
This is a wonderful question, really wonderful question. What he's saying is that he noticed, if you look at the CV here, all right, if we're really saying we only 10 to the minus 19, by the way, we're not talking about 10 to the 19 after all, it's the mismatch. Turns out mismatch is larger than that, even though it's only 1% of the transistor, right? Still, maybe automatically larger than that. But let's just take this. What is telling us is only 1 electron. Can we really believe it? Can ammeter really measure that? First of all, ammeter is not called on to measure the charge in 1 cycle. Ammeter is integrating over a period of time. That's how it gets sensitivity, all right? Okay? And so over that period of time, you're not talking about 1 electron anymore, okay? That's why you get this picoampere sensitivity of 0.1 picoampere. Certainly within the sensitivity of the ammeter, no question about it, all right? So then go back to the physics here. 1 electron, does that really work? Does that not really work? Very interesting question. And I think at some point it will become probabilistic. I think you were forced a little bit to think about this when we talk about telegraphic noise, right? You have this only 1 trap, depending on the trap energy relative to the Fermi level. It says it should be 0.7 electron should be there. How is that possible? It probably means 0.7 time electron is there, 0.3 time electron is not there. Now, if truly each cycle requires only 0.7 electrons, I have to believe what that means is that some cycles you get electron there, some cycles don't electron there. All right. Now maybe there are better ways to think about that, but so we still have to think about average. Okay. Yes.
I guess I can see how the drain capacitances affect your sensitivity because they're in parallel with the capacitance to be measured, but do you know why CGS affects your sensitivity? Because
CGS, if you truly refer to CGS, okay, I guess you're referring to Toure used the term, the delta CGS. Now, if we really look at this statement closely, then CGS doesn't matter because between drain and source, between gate and source, there's no current being drawn from the power supply, all right? And both this CGS, it's really the CGD mismatch, all right? Overlap of the drain capacitance mismatch. Even the source side mismatch, we don't care. That's a good point. Okay? All right. Other questions, comments? All right. So this is an interesting idea to measure the capacitance. In addition, there's a tool called a simulator. And engineers do use a 3D simulator, some fast Laplace equation solver, and here's an example. Some students show that this solver, actually this is not a particularly fast one, actually is not exactly agreeing with the experiment. Of course, in implications, we think experiment data is right, that is the simulation is not quite right, okay? All right. Okay. A very important topic is something sometimes called the deep submicron design problem. That is, interconnect becomes dominating in the circuit delay. And one view is this, is to say, if you plot a delay versus the technology generation, as we make technology generation smaller and smaller, the gate delay is getting shorter and shorter. Gate delay meaning the tau d that we talked about last time is the gate delay, yeah? Right? And this, of course, is to the credit of the very good work that all the device engineer and the process engineer has done. Delay time is getting very short. On the other hand, if you look at the RC or RLC time constant, all right, not even, let's just think of RC in this particular plot, not even RLC. RC time constant, and you can show, of course, you can argue what kind of assumption was used, that actually is getting longer and longer. This is because, line is smaller, therefore arc may be large, right? Maybe a dielectric is smaller, or the capacitance of the neighbor is larger, so C is larger, and also chip is larger, so the interconnect line length is longer, so therefore this interconnect delay gets much larger. All right, and if we use some more advanced material like copper line or even low K based on this plot, well, things just a little better, not so much better. One could say this is alarmist view. I would not say this is incorrect, but I think it's fair to say it's misleading. Because if you look at that as if we're saying, gee, even quarter micron, this interconnect totally dominates. We shouldn't be trying to make better transistors or smaller transistors. And we still do that. Everyone's trying to, compare its competitor. What ID set you get if you read papers, that's what the people compare. So clearly there's a discrepancy between the picture this diagram seems to be showing and what in reality is happening. All right, this seems to be too one-sided. And so let's look at some more realistic pictures and look at some things. A lot of this has to do with assumptions made in a simple plot like that, okay? Okay, that plot did mention copper, so let me just point out. Copper is finally happening, just beginning. UMC is beginning to offer 0.13 micron copper. IBM was the first one to use copper in production. And so aluminum is replaced with copper. As a result, electromigration significantly improved, and also the resistance is also improved. There's a 40% reduction in resistance simply because copper have lower resistivity compared to aluminum. All right? Okay. So copper is one thing. All right. And earlier I talked about low K dielectrics. This is not yet happening, but perhaps in 5 years, a few years, we're going to see low K dielectric. The idea is that instead of using the SiO2, we use some other dielectric material. And this slide was done in, I guess, 1997, so it's already out of date. This hasn't happened as fast, but people are already using some modified SiO2 by adding fluorine, for example. They can manage to get dielectric constant somewhat lower than SiO2. And then we'll be looking into some organic material, and in fact the international roadmap, the small print we can now read. If you really read it, this actually came from the roadmap. It's projecting that eventually we're getting lower dielectric. Eventually there's a concept of air bridge, all right? There's really nothing between the metals, okay? All right. Let me just, okay. So, yes?
Didn't you just show us a picture, though, before, where they threw it in acid and took out all the dielectric?
Yeah, so that's the idea
Can you
that
do a
it
similar
might be
thing
done.
here?
You may say, hey, gee, why don't we just go ahead and do that? The problem is if you do that, do we really know that after some operation, these wires won't bend all out of shape and touch each other? Remember what you said about electromigration, how violent the force is? We're counting on this oxide to keep them in place, really. Now, if you take them away, can you really trust to leave them alone? All right? I don't think shaking vibration is going to be a problem, but internally it's a lot of force. Now think about moisture. Right? Moisture is something that can always give us problems, corrosions and other problems. Now when you expose this metal, all these large surface areas, if you capture surface area, I have never calculated this, my guess is going to be several square meters of surface areas. How much moisture can it absorb? And what's that going to do? And so there's a lot of questions. Not necessarily. Today we don't do that. You can say we trade off. We're going to invent a vacuum pack for this. We don't do that today. In fact, we just dip the whole thing into plastic, for example. Plastic is dirty and it's permeate to moisture. All right. So certainly there's a lot of challenge, but it may still happen. So this, the story is still unfolding. It's exciting. Okay. All right. And so I'll review one study trying to put a more sort of interesting spin to this, or try to get some more useful information rather than just say, gee, if you compare the worst case metal line, certainly that is the worst case, no questions about it. But can we find some more interesting insight from this analysis of the interconnect? So this was done by a student, Dennis Sylvester, who is now a professor at University of Michigan, and Professor Kurt Koiser here. And so what they did is they first look at 13 actual design circuit. Get the net list, look at that. Consider all the nets. And they concluded average length is 360 angstrom, and average fan out of the gates is 2.69. And in fact, they did the statistics, and found out the ones 55%, found 2 some percent, and the lengths, and do all that. So after analyzing this kind of raw data, they decided that there's a typical critical path logic. Depth is 14 gates, and this typical critical path is made of 8 fan-out equal 1 gates, 3 fan-out equal to 2 gates, 2 fan-out equal to 3 gates, and 1 fan-out equal to 4 gates. In addition, an optimally buffered global wire is included, and the wire is proportional to the chip edge. All right? Think about that as a typical critical path. And of course, you can also construct your favorite typical path. Yes?
What's fan out?
Fan out meaning if you have an inverter, its load is the stage being driven by it, right? Now if it drives only another stage, we call this fan out equal to 1. All right? But certainly possible this signal is used to drive 2 gates. You see that? In that case, we call it fan out equal to 2. So fan out equal to 1, fan out to 2 really makes a difference in the load capacitance. Okay, that's why in our delay model we have the C representing all the capacitance. We're not really limiting it to any case. Yeah. So through this kind of study, they just pick this one particular critical path as critical path. Okay, and you're welcome to construct your own, but methodology is this. And then calculate the delay, and in fact even consider the impact of neighboring signal activity on the switching delay. All right? You can see if the neighbor is suddenly changing, it's going to have impact on the delay time. You see that? All right? And this is important because what they're trying to do is trying to construct a crystal ball and to learn something about the future trend about interconnect versus device, or what's the best way to make use of strengths of each, and how we have to rethink the way we use the interconnect, use the device, right? And so a lot of details are considered. And then you end up with this kind of a result, okay? And the bottom is the process generation. Of course, Dennis has to use his device technology and being able to predict what he thinks the future technology transistors are. For example, he needs to use the kind of model that we talk about, in fact, exactly the same model we talk about here for the ID set, right? Because that, or the delay model, because that's what's required. You see what I'm talking about? Okay. So here is plotting several things against technology generation. And let's look at left-hand side is the delay, and that's the, and delay is the, let's see, what is, okay, it's the same scale, left and right, same scale. 2 bars. The darker bar is the gate delay, The lighter bar is the stage delay. Now I have to clarify what this means a little bit. Gate delay, he refers to the transistor delay, the device delay. If there was no interconnect, what's the delay? Okay? Stage delay means if there is a interconnect line, okay? All right, with interconnect. And the interconnect, unfortunately, I forgot what is the interconnect specific links used here. I don't think Kevin remembers. Kevin, do you happen to remember in this case the interconnect length?
For this map?
For this particular plot? Yeah, it's a something considered later. I will tell you what this conclusion is. Is within one circuit block. You know, one technology design methodology in the future is that the chip will be made of by many blocks of circuits. Each block can be an IP block or a fairly large circuit designed by itself. In fact, a whole CPU will be one such block. Each of this block, however, probably only would be 100 micron in length. It's not going to be the entire chip. The chip may be getting very, very large. This block probably will not get larger. In fact, may get smaller because we're scaling things. You see what I'm talking about? Okay. So he's just using this line, this entire line of this block. And so what's interesting is that, you know, the interconnect portion actually becomes smaller percentage of the device delay. Okay? See, this difference between the dark bar and lighter bar is interconnect. The difference becomes a smaller percentage of the dark bar itself. All right? All the delay is getting better with scaling. That's good news. And interconnect, in fact, is not getting larger within the limits within a circuit block. Okay? And circuit block about, let's say, 60, 100. 1,000 of gates, and it's a very large circuit. 100,000 gates is a very large circuit. So within this block, it's actually interconnect is not getting larger. Okay. All right. So I'll do that. So therefore, one can simplify the interconnect problem in the following way. In the visualize, the chip is going to be made of many of these the circuit blocks. Within a block, turns out the old way of designing circuit is not too bad. That is, we don't have to totally change the device-centric view of or style of circuit design. Once you designed these blocks, these IPs, then there needs to be much more care in the place and route to connect these blocks. But the problem is now simplified by many orders of magnitude because you only have maybe a few hundreds of blocks as versus billions of transistors. So the picture is considerably simplified. All right. So therefore, it's important to remember the interconnection between circuit blocks is going to be very important, and the potential things that people can do will be things like optimum, let's say, buffering devices, stages. Turns out the delay time is a little shorter if you break one large interconnect to two interconnects with a amplifier in between, all right? And this has a smaller delay than that interconnect. So depending on the length of the interconnect, you may even break into two. And so other ideas would be for these type of interconnect between the blocks, we would dedicate a layer of metal which we use fairly thick metal to minimize the resistance, and we also use fairly low density metal lines, so the distance gap between the metals is large, so don't have much capacitance. You see what we're talking about? Because the density now is much less now. You're only trying to connect a few hundred of blocks rather than millions or billions of transistors. So by doing this, now the picture doesn't seem to be as bleak as one might have concluded just by looking at that one simple plot of the transistor delay versus the gate delay, versus the interconnect delay. It's okay? Other questions about interconnect? All right, the last slide I prepared just try to summarize this a little bit. There's the technology solution. There's the copper, 30 to 40% low resistant aluminum, which is beginning to happen. Low K dielectrics offer 20, 40% or maybe even more improvement, and but this takes time for this to happen. Design solutions is even longer, so design side certainly is very important. And there's the ratio of interconnect delay to device delay will not rise with technology scaling within a circuit module or IP block, all right, of about 100 kilo K gate or IP module, all right? So one can then concentrate on the interconnection of the IP modules. Special design effort necessary for this really global routing among the IP modules. There's the device sizing. So today we talked about, at the beginning of today, we talked about the optimum size for WNWP, is that right? Right? Okay. So if you really want to drive very large interconnect, you're going to use some very large transistors. You're not going to use very small transistors to drive large long line. So if the transistor is very large, then you cannot say the transistor capacitance delay is not important. All right? You have to keep that in mind. In other words, capacitance will not be dominated by the interconnect. In fact, the optimum is when the transistor contribute half of the same amount of capacitance as interconnect. Remember, this is one conclusion beginning of this lecture, today's lecture. All right? So one simple conclusion. That would be device sizing is important. Using perhaps, we're not going into detail, but just because this density is not so large, you can play games with wider wires and either taller or flat wire. Turns out also have other benefits. A tall wire will give us low resistance, but I can also use a wide wire to get low resistance, right? By using wide wire low resistance, I can use thinner or flatter wire to minimize the capacitance with the neighbor. You see? So that requires a detailed knowledge. How important is the capacitance relative to resistance? I may decide to do this, right? And that hasn't been discussed much, but this is one conclusion that we came up with. This in cases, this actually may be better. Certainly the pitch should be carefully optimized. The standard design style still is that width and the gap is the same, right? And we want to see how we can optimize that. Repeaters, very important. That's breaking wire into several steps. What's interesting is that most of the studies, including what Kevin has shown, one really doesn't want to use too many repeaters. Actually, does not require that many. One repeater, most two, is really good for the largest chip. So this is a little different from the view some people hold. Consideration of interconnect and communication in architecture, flooring plan plays a role. Is really where the game is going to be. So that concludes the discussion about interconnect. Okay, questions, comments? Some of you probably have some personal experience with the interconnect, and any experience you would like to share? All right, if not, then I'll see you next week. Let me remind you, reading, okay?